Okay, thank you. Is the mic working all right?
No.
All right, great. So I'm really excited to be here at this wonderful conference and to have a chance to tell you about some work I did with my collaborator, Katherine Brown. We also benefited a lot from conversations with Stacey McGaugh, but of course, he's not responsible for any shortcomings in this work. For that, you all guys are going to blame each other. So maybe this isn't necessary, but I'd just like to quickly remind you about a brief history of the discovery of planets in the solar system. So it starts with the 1600s, when theorists had proved that there are only 6 planets in the solar system. So it's a nice reminder that theorists sometimes get a little bit ahead of themselves, but even the very best ones. But of course, nothing destroys your theory that there are 6 planets better than the discovery of the 7th one. Now, this one was discovered by chance, but then Neptune was actually predicted, and so it's a real triumph of the whole beautiful mathematical theory of perturbations, and this is of course a very well-known story. But at the same time, in the 19th century, when the outer planet orbits were a clue to the existence of Neptune, there were other anomalies also in the solar system. There were anomalies in the orbit of Mercury, which led to the hypothesis of a planet named Vulcan. But as we all know, of course, now, the resolution was that near the sun, fields are sufficiently strong that GR corrections matter. So in this case, it turned out to be modified gravity was the explanation. And then there were anomalies in the orbit of the outer planets as well, which led to the prediction of a planet in the outer solar system. At first, people thought it was Pluto, but it turned out to be far too small. And in fact, in this instance, it turned out that improved data showed that there were actually no anomalies at all, and everything was working just fine. So all of these outcomes can happen. You can discover new gravity, new planets, or nothing at all. And that's worth keeping in mind. Now, what Pluto was, of course, was not a planet, but it was really the first Kuiper belt object that was discovered. And but no further Kuiper belt objects were discovered until the 1990s. Until the 1990s, when the first one was discovered, the second one was discovered, and since then thousands more have been discovered, which is kind of exciting when you think about the pace at which the field has advanced. So, I guess the thousands of Kuiper belt objects are classified into 4 families. They're the ones that are in resonance with Neptune. They're the ones that are sort of in similar orbits, the classical Kuiper belt. But maybe the ones that are of most interest to us are the so-called scattered disk. And actually a very specific subset of these, of which there's a Sedna was the first one. So these are Kuiper belt objects that are quite well detached from the rest of the solar system. So their orbits are really dominated by the sun, and even the big outer planets are a very, very small perturbation of these. As I said, Sedna was the first one. It was discovered in the early 2000s. The second one was discovered in 2014, as you can see from this. That's 2012 VP. It was actually discovered in 2014, confirmed in 2014. But since then, dozens more have been discovered. And our hope, of course, is that many, many more will be discovered. The reason these are of interest is because they make excellent tracers of, the kinds of phenomena that we want to study here. But first, let me tell you the conventional story about these objects. So the Sedna family is believed to have quite anomalous orbits. And here you can see one of the anomalies. You should focus on the purple ellipses over here. So what you notice is that the Sedna family orbits, first of all, they're all highly elongated, which is unusual. But the other thing is that they're all fairly well aligned. I mean, it's not like they're all pointing in exactly the same direction, but there's a preferential orientation for these orbits. And so that's led planetary scientists to propose that there might be a 9th planet in the outer solar system after all. And so that's the planet 9 hypothesis, that this anomalous alignment of these orbits, it's another anomaly over here. Well, actually, let me tell you about planet 9 first. It's conjectured to be about 500 astronomical units from the sun, and to have a mass in the range of 5 to 10 Earth masses. And I guess this might be a good moment for me to remind you that a planetary orbit, it's characterized by 6 orbital elements. There's, of course, the semi-major axis, which tells you the size of the orbit, the eccentricity, which tells you the shape, And then you have these three Euler angles which tell you the orientation of the orbit. And finally, of course, there's the eccentric anomaly which tells you where on the orbit the planet actually is, or the Kuiper belt object actually is. And this is an example of the kind of data that you see. You see the Euler angle omega over here, plotted as a function of semi-major axis. And you can see that the ones that are inner, in the inner solar system, they are completely randomized in omega. But as you move outwards, they have a preferential value of omega. I mean, on the whole, I prefer to show the orbital alignment rather than omega, which is really frame dependent. So, but this is how planetary scientists like to plot their data, so I wanted to show you. Okay, in any case, so this is the Planet 9, evidence for Planet 9, and the conventional evidence for it. Now I want to switch gears and talk about a possible MOND interpretation. And I should say, yesterday we heard that the EFE in the solar system might not be a universal property of MOND. So I should say that this work is firmly based in, in QMOND and in the modified gravity interpretation. So if we start with Newton's laws, you can write them as by analogy to electrostatics. The gravitational field obeys Gauss's law and is curl-free, and the force on a test mass is just the gravitational field times the mass. If you look at QMOND, what happens over here is that you amp up you modulate the Newtonian gravitational field with the interpolating function, and you obtain this field GP. And then the physical field, the quasilinear field GQ, is the curl-free part of GP. So that's quasilinear MOND in a nutshell. And of course, the interpolating function, as everybody knows, has to have these asymptotic behaviors in order to generate the correct rotation curves, galactic rotation curves. In between, I guess there are various options, but we've done most of our illustrative plots using this interpolating function. But I should emphasize that there's nothing specific to this interpolating function in the results I'm going to tell you. So for a point mass, of course, you get 1 over r squared behavior or 1 over r behavior, and the crossover radius is the MOND radius. The interesting thing is that for the sun, again, as is quite well known to this audience, the MOND radius is about 7,000 astronomical units. So that's big, but it's not. I mean, it's kind of exciting, really. There are no planets, obviously, out there, no known planets to serve as tracers. But one could imagine outer Kuiper belt objects like Sedna potentially proving this physics. Most of those are at a few hundred to about 1,000 AU. So they'd be in a sort of small perturbation, but it would be a deep MOND regime, but it's potentially accessible. Okay, so if we look at, if we try to think about the outer solar system in context of quasilinear MOND, in Newtonian gravity out there, the gravitational field is dominated by the sun and also by the field of the galaxy, which you can treat as essentially uniform. If you were moving out to the Oort cloud, you might need to worry about tidal effects from the galaxy, but within the Kuiper belt, you can treat it as essentially uniform. Now, of course, in Newtonian gravity, the gravitational field of the galaxy has absolutely no physical effects because everything undergoes that uniform acceleration, so the relative motion isn't sensitive to it. But in MOND, you can, again, so we're following Milgram's original papers, you can separate the physical field into the field of the sun plus the asymptotic field of the galaxy. This would be the physical MOND field of the galaxy, not the Newtonian field. So that's why I call it gamma sub G now. And then there's whatever else there is, and that's the anomalous, the anomalous field. This is the external field effect, the fact that this exists, this anomalous field. And of course, we've heard many talks at this conference about observations that may or may not have detected this effect. So you can interpret the anomalous field as the Newtonian field produced by the phantom mass, which is given by this expression ultimately if you trace through all the definitions. And just so you can see what the phantom mass looks like in this context, it's basically an anisotropic shell which is at something like the MOND radius. It's actually about 0.3 times the MOND radius is where it peaks. And it's not really like a thin shell. It's got a long tail out to infinity. But it does plummet to essentially zero mass density in the inner solar system. So that's more or less what this phantom mass distribution looks like. It's rotation. I should also said in this plot, well, like it already says so. This is just a cut to the XZ plane, but it's rotationally symmetrical. So that's how you can visualize it from this heat map. You can also see that point over there where the galactic and solar field cancel each other, although that's not too important for what we're about to discuss. So the field in the inner solar system, when you have this mass distribution out there, you can make a multiple expansion. And just by on dimensional grounds, the quadrupole expression should look something like this. The solar mass is the only relevant mass scale over here. The MOND radius would be r cubed, and then r is how far you are from the sun. And it has a T2 behavior, so that's just quadrupolar field. So you can go ahead and estimate what the strength of this quadrupole is within QMOD. And then you can compare that to the field of planet 9, which would also, if you orbit average, planet 9 is pretty far out too. So in the inner solar system, that would also look like a quadrupole. And this is kind of our second clue that maybe MOND may have some bearing on these Kuiper anomalies, because the quadrupoles actually come out to be comparable in magnitude, in order of magnitude. They do have the opposite sign though, so of course the physics is going to be interesting and different, and that's nice, it gives us something to do. Okay, so here I just explained what I already said, that if you're interested in the effects of planet 9 in the inner solar system, you want to treat it like some mass distribution, which is kind of the orbit average version of the planet. You imagine that you have an ellipse of mass, and the mass density that he places proportional to how much time the planet spends in that part of its orbit. I should also mention over here that in the course of doing this work, we had to immerse ourselves in this whole 19th century technology of planetary perturbation theory. And we found a new way to calculate the multiple moments of the disturbing function. I'll come back to, in case your planetary perturbation theory is a little rusty, I'll come back and remind you about that. But I did want to advertise that we found a new way of calculating the multiple moments of the disturbing function. So it was kind of fun to add to this 19th century lore. And so you can calculate it to arbitrary orders using our method. And this might be useful. This is of course useful for the work we're trying to do, but it might also be useful in general for planetary perturbation theory and where technology we have we use it. So yeah, I guess I'm going to now talk a little bit about orbital dynamics, which is still relevant and useful. It even had a cameo in this recent movie. So what's the basic idea here? So under the action of the sun alone, the Kuiper belt object would pursue a Keplerian orbit, which would be characterized by the 6 orbital elements. And then under the influence of planet 9 or MOND, the orbit slowly evolves in terms of these orbital parameters. And that's described by these equations called Lagrange's, confusingly enough, they call Lagrange's equation, although they've got nothing to do with conventional Lagrangian mechanics. The dynamical variables over here are the orbital elements themselves. And so this is in contrast to Lagrangian mechanics, where the variables come in pairs. You have a coordinate and its associated velocity, or in Hamiltonian mechanics, where you have coordinates and momenta. There's certainly no sense in which these can be paired up quite so simply. But it's similar to Hamiltonian mechanics. We work with something called the secular approximation, which leads to a couple of other simplifications. Here you're looking at the long time behaviors, so you don't really care about, the planet or the Kuiper belt object is just racing around the orbit, and you don't actually care where it is on the orbit. So that variable drops out. And also in this approximation, the semi-major axis doesn't change. The overall evolution is then controlled by something called the disturbing function, which is the Hamiltonian of this kind of dynamics. And it has a very simple interpretation. It's just the orbit average potential energy of the KBO, of the Kuiper belt object, in the field produced by the phantom mass, or by planet 9, as the case may So this is the thing that we can calculate in a multiple expansion. You basically treat the field of the phantom mass for planet 9 through a multiple expansion, and then you calculate the potential energy averaging over the orbit of the KBO. And for example, this is the quadrupole expression, and we also have the octupole. We needed both of those. I just wanted to show this one to gloat over the fact that we can get exact expressions, but I won't impose the octupole on you. So the one thing you'll notice though about this disturbing function or this potential energy is that it's independent of the Euler angle omega, and that just reflects the rotational symmetry of the problem. And this might be a good place for me to be very clear about what coordinate system we're using. So the sun is at the origin, the center of the galaxy is along the positive z-axis. And then the Euler angles work in this way. You start from a standard orientation where the KBO orbit lies in the xy plane and the perihelion is along the positive z-axis. And then you get to this orientation described by those angles by first twisting the orbit about the z-axis by little omega, then about the x-axis by the inclination I, and then finally about the z-axis again by big omega, and that gives you the orientation that's described by those Euler angles. So because of the rotational symmetry of the phantom mass distribution, the cylindrical azimuthal symmetry, the angular momentum along the z-axis is a conserved quantity, and it's basically proportional to the eccentricity and inclination, or depends on the eccentricity and inclination in this manner, the z component of the angular momentum. And of course, the disturbing function, like the Hamiltonian or energy, is also conserved under this dynamics. So this is a system where we have three Euler angles and the eccentricity as a dynamical variable, so 4 degrees of freedom, and 2 conservation laws. So it's an integrable model, and that means we can solve it exactly. So what we've done over here is we've gotten rid of so let me just go back over here. We've gotten rid of the inclination using the conservation of h, and so we just focus on E and omega. Of course, nothing depends on big omega. And what we want to show with these contours of constant energy or disturbing function. And so the KBO, its dynamics in the E squared omega plane is just going to be along these lines, along these contours. The interesting thing you see is that as the z component of the angular momentum changes, there's an abrupt change in the dynamics. At first, it's not very interesting. All it does is it sort of precesses in little omega, also in big omega, it turns out, and of course I've eliminated it from the problem, but physically it's an important thing to ask what's happening with omega. It precesses in both of them, and it just bobs up and down a little bit in eccentricity. But when you have low angular momentum along the z-axis, then you get these 2 fixed points. And so that if you're close to them, then you'll just be the stable fixed points, both of them. Now this is in the quadrupolar approximation. What happens when you take the octupole approximation into account? Well, in that case, the effect of the octupole is that one of the fixed points becomes less stable than the other one. And then, of course, you have to ask what happens with all the other perturbations that we've ignored, the giant planets, the non-secular terms, the motion of the sun around the galaxy. Well, we know from the general theory of Hamiltonian chaos that what's going to happen is that the whole phase space is going to break up into a chaotic flow, except near the stable fixed points. There may be, if the perturbations are not too strong, you would still have a stable flow over there. And so this leads to our prediction that there might be a population of KBOs whose orbits are described by the stable fixed point. So what would that look like? Well, what that would look like is, what we find is, again, if you're dealing with small angular momentum, the inclination would be close to 90 degrees. And the Euler angle omega is equal to minus pi over 2. So if you again think back about what kind of orbit orientation it corresponds to, that means that the orbits, the perihelion is going to be towards away from the center of the galaxy. So the orbits are big ellipses. If you draw, this is called what we call the apsidal vector, alpha k, the unit vector from the sun to the KBO perihelion, and that's going to be pointing away from the center of the galaxy. Actually, that's very intuitive because the KDO spends most of its time when it's far from the sun on the orbit. So that's the heavy end of the orbit. And so that's going to hang towards the center of the galaxy because that's where it's being attracted to. So that's our prediction, that the apsidal vector should be pointing away from the galactic center. And so now we can go and look at the data. So we look at the 6 best known examples of the Sedna family. We look at the orbital parameters over here. And then we can go ahead and calculate we can go ahead and make a plot over here. So this is just in the ecliptic plane, but the orbits lie pretty close to the ecliptic plane. So if you look at them in 3 dimensions, they just lifted off this slightly. So the projections are not very distorted. And you can see the alignment, which you could also see in the plot I've shown you earlier from the planetary science paper. But the additional feature that you see in this plot is that we've drawn this arrow towards the center of the galaxy, and you can see that it lines up. And that's something that happens only within MOND. It would be a pure coincidence within planet 9, and it would require planet 9 to be currently in that location, which could happen, but in MOND it's actually an actual prediction. So we thought that was pretty exciting. Now the other thing is, of course, you only have 6 objects, so it's it's too soon to claim that this is a discovery. The odds are about 1 in 200 that this alignment is purely by chance. So if this was a horse you were betting on, I guess those are pretty good odds. But proving a scientific theory, maybe we need to wait a little bit. The way we calculate those odds is just by the usual usual tests. So the conventional hypothesis would be, null hypothesis would be that the alignment of these apsidal vectors with the center of the galaxy is uniformly distributed. So as against that, I show a histogram of what we actually see with the data, and you can see it's not very close to being uniform. But again, if you calculate the probability of this with the null hypothesis, it's 1 in 200. And that's just because we only have six data points. There's also a clustering in phase space, which is a little bit more subtle. And here, I'm just going to show you where the 6 objects fall. So what's plotted over here, the red points are the actual eccentricities of these objects. And we've plotted that where 3 pi over 2 lies, because that's where the fixed point is. So we expect them to be close to this fixed point, to the corresponding fixed point in this phase space. And indeed, those blue points show you that they're quite close. I guess the null hypothesis over here would be that they could be anywhere in this rectangle, and we see a pretty strong clustering, although we haven't quantified that. So, in short, what we really need is a larger sample of Sedna family objects, and maybe we need to go a little bit beyond just doing this analytic perturbation theory. So that's our future goal, to carry out dynamical simulations where we can actually quantify how large of an angle we expect typically. They're not all going to be perfectly lined up. Just get a distribution of that and compare that to a larger sample. And the prospects for doing that are pretty good because there are all these ongoing and future surveys. And so if all goes well in a few years, we should have hundreds of these objects. And one way or the other, we would know what's going to happen. And so I guess we should, this brings me back to the beginning of the talk, which is that at this point, the clustering, because there's so limited data, it could be due to planet 9, or it could be much more exciting due to MOND, but it could also be spurious, as we've seen historically that's happened. It could be an observational bias, for example, which a number of people have argued. So again, I want to underscore the fact that historically we've seen all these things happen, that they were just observational errors, but there were also dramatic payoffs with anomalies in the solar system. And so I think the most important takeaway over here is that the Kuiper belt is a laboratory for studying fundamental physics, and especially MOND. And we will, I hope in a few years, tell you what the outcome is. Okay, thank you very much.
Thank you very much. So we shall take questions special language. So, what exactly defines Sedna-like objects? And the other thing, was my impression correct that you're saying that some should be trapped near this fixed point, but not all of them perhaps? So what is the...
Yeah.
So do you expect all the ones that, to be aligned in this way, or that there should be some peak in the distribution?
Yeah, I think so the expectation, and I guess the dynamical simulations are essential to really properly answer your question, so I'm speculating over here. But first let me go back to your first question, which is what defines Sedna family objects. It's objects where the inner solar system is a relatively negligible perturbation. So the physics is dominated by the sun, and in MOND also by the galactic field as well, for the quadrupolar producers. That's sort of an operational definition. I guess the way that people in the planetary science community define it, they look at the orbits and whether they're stable under all the perturbations, which they can incorporate in the simulation. So that's again the same thing as saying that the perturbations of the planets are small. And that's why we only have like 6 that are definitely, Sedna family. Because in fact, if you just go and look at things that have big orbits, there's about 15 or 20 in the planetary database. But we don't have the resources right now to test the stability of those orbits, so we've stuck to just the 6 that have been embedded. Now to your other question, do we expect all of them to be at this fixed point? Yes, I think so, because I mean, if you imagine like, billion years ago, they were injected into all possible orbits. If they were in the chaotic orbits, they would have been kicked out, out of the solar system or in the solar system, and they wouldn't be, in stable orbits where you could be observing them for a long time. So that's why we expect a family where they persisted for a long time.
Another question?
So a quick comment, and then I'll ask the question. So the Sedna-like objects are defined as having a perihelion larger than 40 AU, I think. So if they were undergoing Keplerian motion, they would never get close to the planets. So these are sort of detached Kuiper belt objects is another name for them. And that's important because it's hard to understand why they would have such a large perihelion if they were scattered out by any of the known planets in the solar system. But what I wanted to ask is, can you go back to the graph showing like the eccentricity against the, this one. Do you have any idea what a graph like this would look like in the absence of the MOND external field effect? Like, would they still cluster close to, at least would they still cluster close to high eccentricities? Would that at least
I don't think there's any reason to expect them to have high eccentricities in the absence of either MOND or Planet 9.
So neither the high eccentricity nor the clustering of omega k around 270 degrees would be sort of expected in that scenario.
Right, that's right.
Okay, thank you.
Very nice work. You mentioned the possibility of observational biases. Could you comment what actual biases could lead to clustering of this type and the orientation along the center of the Milky Way?
Yeah, well, I mean, I guess the observational biases are first about where the surveys are looking in space. Also, there's another bias, which is that these objects are always discovered when they're closest to the sun, because they have these enormous orbits that go far out. So that introduces a bias as well. But frankly, we haven't looked so much into this question about observational bias because we'd just rather wait until there's hundreds of objects so that we don't have to have this argument about whether the data that exist are biased or not. But again, I should say that there's a big, just in terms of reporting, so I'm just a spectator here, but the planetary community, they're divided into this camp that believes it's all observational bias, and then Planet 9 people who say, well, there are enough different surveys that they all have different biases, and this is good. I feel like this is one of those arguments, why not just wait?
I'm not familiar with whether this is likely to be a real clustering or not, but what I've heard is that the main type of observational bias that will come in, as you were saying, is related to like the higher discoverability in the perihelion, but the reason this is not uniform in angle is apparently because it's easier to observe in some seasons than in others, and that makes it easy to discover objects with perihelion in certain directions of the sky. I don't know how believable that explanation is for this clustering. There are surveys which have a more homogeneous sky coverage, which are designed to get around this issue.
Yeah. Yeah, for example, the Vera Rubin is coming online, and that's going to have absolutely no biases. It's going to look at everything, so we won't have to discuss this anymore.
Just as a quick comment concerning future observation, I think possibly Euclid can be of help for this kind of objects, and considering that the observing strategy is not biased, that it's quite uniform, and will be deep both in the optical and the near infrared. So have a look.
Yeah. There's also a really unusual idea of using CMP S4 to look for these objects as well, because you can see through transients in the microwave. That's where these objects radiate naturally. So yeah, there'll be a lot of different observational schemes in the future.
Okay. I'd like to ask a question myself also. Some years ago, there was an investigation of the planet 9 or X using very accurate planetary ephemerides. The INPOP ephemeride is a Paris group, and they showed likely direction for the planet X. But unfortunately, this is not in the direction of the galactic center. Are you aware of this? And so
no, I have to look into that. Yeah. However, I mean, we don't require, we don't really care so much where planet 9 is, but our prediction is that the apsidal vectors should be lined up with the galactic directions, and that seems to be, pretty, that seems to be true regardless of where planet 9 might be. But I better check out this paper. Yeah, thank you.
thank you. Okay, so we thank the speaker again.